forecasting applications. And I'd like to introduce the session chair, Dr. Adria Brooks, who is the Director of Transmission Planning at Grid Strategies.
Thank you, Debbie. Thanks everyone for being here. Welcome to Nashville. I grew up here, so I feel somewhat obligated to say that. Although I haven't lived here in 20 years, so don't ask me where to eat. If you want music recommendations, though, that I have. I'm really excited for the panel tonight. Thank you all for being here for the whole day. We're going to talk through a whole lot of different applications. So first, applications of forecasting of weather as it relates to power system modeling. And then we're also going to talk solar, wind, hydropower. We've got a little bit of everything up here. So first, please welcome Professor Tom Overbye of Texas A&M. I first met Tom when I was a grad student several years ago, so excited to get to hear him again. Thanks, Tom.
Okay, thanks. I'm really happy to be here. I'm Tom Overbye from Texas A&M, and I'm going to talk to you not so much about doing forecasting, but using forecasts and other weather and environmental inputs in power system planning. So my background is I'm a faculty member, so I teach power system classes, but I also have a company called Power World that develops software that's used for electric grid planning. So mostly transmission planning, longer term planning, and we have power system analysis tools like power flow and optimal power flow and contingency analysis. So in that, we were thinking with all this growth in wind and solar and with the line ratings becoming much more dynamic, how do we deal with this in the planning context? And we were doing a project at Texas A&M, actually for Southwest Power Pool, looking at the interconnection of the eastern and western grids AC and whether that would work. And the takeaway from that is it would work. But we had to do these large power flow models on, 120,000, 130,000 buses, thousands of generators, many of which are wind and solar. We're like, how do we figure out what the dispatches on these things are? And we're like, that's really kind of hard to do. Then we thought, well, maybe we should just directly incorporate weather data. So that got us moving in this direction. I was also working on a project for ARPA-E where they were doing the grid optimization competition, and we were developing data sets for them, synthetic electric grids. And we had to make up realistic scenarios for these 10,000 bus cases, power flow cases, and dispatch the generation. And again, how do we do that realistically? And Dick O'Neill, who ran the project, he said, look, you can't have a scenario where it's nighttime and all your solar's running. So we're like, yeah, we kind of have to incorporate this weather information into the power flow. So that got me going down this path. The gist, as everybody here knows, is the electric grid depends on the weather, depends on it from a load perspective. And of course, now it depends on it much more for wind and solar as well, dynamic line ratings. So we need this information. Of course, we've been using it in real-time operations for a long time. And actually, one of my first jobs was in Electric Grid Control Center back in the 80s, and we were bringing in lightning data and radar data, and my senior design project was actually bringing weather information into Electric Grid Control Center. So I know it's been used for a long time, but it isn't used in the planning application. So that's what we've been working on and have been made a lot of progress on. So the gist here is planning, and of course, planning is forward-looking, and it can go from very short-term, like sometimes we use our software for, almost real-time operations. Sometimes it's near real-time planning. Sometimes it's decades out in the future. So you have to take into account the availability of information. And of course, when you plan, you have to plan just not for the good days, but you also have to plan for the bad days. So you have to account for really bad scenarios. And when we talk to customers, they'll be like, yeah, we need to deal with geomagnetic disturbances and wildfires and ice storms and all sorts of bad things. So we are working on doing that. Lately, as in the last couple years, the power flow has finally changed in the sense that you can do power flows without geographic information. And that's been done for decades, and there are good reasons for that. But it is now changing that the power flow models have geographic information for the substations, which lets us know where the buses are and the generators are. And of course, that then opens it up to a wide range of other applications, including integrating in weather information and other environmental inputs. My start on this, I am a power system guy. I'm not a weather guy. So we started out just kind of using historical weather information. But then as we talked to our atmospheric science people at Texas A&M, they were like, yeah, you should use some of the reanalysis data. So we've gotten into that. We're using now the HER data and also the ERA 5 data. In my journey in this process, ESEG put out a really great report in October 2023 on weather data set needs for planning and analyzing modern power systems. So I commend those of you who were involved in that. I think that was a great report. Here's a couple of quotes from that report. Certainly the report says it's important to do this. And I like that they say in the report, the work required to achieve a long-term solution to weather data needs is not trivial, but it is manageable and is much less costly than blindly building trillions of dollars of infrastructure without the basic tools to cost-effectively optimize it and assess its reliability. We certainly concur with it's a challenging problem. We don't think power system planners are blindly building trillions of dollars of infrastructure. So we kind of disagree with that statement, but it's a great report and I've used it a lot. Whoops, I guess I finished up pretty quick. So we have been taking this data and bringing weather data and other environmental inputs and bringing it into our power flow packages. And to do that, we need the weather data. Of course, weather data comes in different formats, and I'll get to that in a second. But what we do is we convert it into a standard format that we call the power weather format, PWW files, and then that lets us use it in the software to map into our power system infrastructure. We have been talking with different customers and they say, you know, you really need to read some of these more raw formats. So we have recently been working on reading the GRIB formats, so we can directly import GRIB files or GRIB2 files, which allows us to take some of the forecasts that people here produce and use it. We have been using the ERA 5 data and also the HER data most recently. Okay, so I won't go through ERA 5 because a lot of people here are familiar with ERA 5. You know, the ERA 5 has nice advantages in that it goes back to 1940. The disadvantage, of course, is ERA 5 has a pretty high spatial resolution, about 30 kilometers. That's not good for a lot of things, but you know, if you're a planner and you're looking 10 years out, maybe it's good enough for what you need. So maybe you don't need super high resolution. Okay, so we actually at Texas A&M have a website where we take this data and convert it into a format that can be used in power flow analysis, and we make this available. And we've done this for North America going back to 1940. HER data, it's been mentioned. A lot of you are familiar with HER data. HER data has a 3-kilometer resolution. So this is data that we also use. You know, you're dealing with a lot of data points when we do the HER and we load it up as 1.9 million elements. You know, if you're doing a large grid, like when we did the Southwest Power Pool project, we were looking at North America coast to coast. So we needed essentially all this data. But if you're ERCOT or WCC or just a utility in that footprint, you need less data. The goal, of course, in doing this isn't to focus on the weather per se, but rather it's to say, how does it affect the grid? And, you know, of course, a lot of your experts in that and saying, I'll take wind data and tell you what the output of your wind turbines are. And that's something that we need. So we are really consumers of the data that a lot of you produce. But what we need is we need to have weather input, and then we need to have ways of mapping it to the grid infrastructure. And then we have to have models that relate that weather. And we're also working on other environmental inputs, like we've been working with the civil engineers on earthquake vulnerabilities, and wildfires are a concern to us as well. So what we've been working on is developing what we call power flow whatever models. They used to be power flow weather models, but we generalized them. We call them PFW models. And these take weather inputs or other inputs, it could be earthquake data, and tell you how it impacts particular electric grid components. And the model that we use for this is actually what the power industry has done with stability code for a long time. And that is you have a portfolio of different models that relate one thing to another. For example, in stability, we might have an electric machine model, we might have a generator exciter model, a stabilizer model, a line relay model, and that's what we're doing here. And actually, we're leveraging a lot of the same code to do it. This is just an example. One of these simple models is just a wind power curve. We've used generic models, but we can also use very specific models as well. That allows us to take the wind data at a location, and then it tells us the power output. And again, a lot of our applications are longer term planning. And when you're a longer term planner, you might be looking at building a wind farm where there is no wind farm. It's a new wind farm. So there's no data, there's no historical data on the power output of that plant because it's new. So you have to look at what the wind is in the vicinity. And, you know, of course, how much resolution you need, how much detail you need is different than what you deal with in operations. This is one of the examples of the model where we've been, again, as I mentioned, dealing with earthquakes, like we might do peak ground acceleration and use that in a planning sense. We need ways to map the electric or the weather data to the electric components. The higher the resolution you have, the better. If it's ERA 5, it's not particularly good, but when you get to HER data and it's 3 kilometers, for a lot of applications, it's enough. And I know that, of course, with wind farms, if you really want to know what's going on in real time on a wind farm, you're going to need more higher resolution because 3 kilometers isn't enough. This is just a slide I have on dealing with real-time terrain. That's an example where we'll take in our power flow model. So this is a power flow planning model, and we load up the HER data, which gives us 3 kilometer resolution. And this is the Pacific Northwest with the 3 kilometer resolution wind speed, that then a planner might want to look at a historical condition and play it forward. Or we're working with our atmospheric science department at Texas A&M to develop future scenarios on how things might change in the future. Lots of different models to be developed. So we are moving forward on this. We're hoping to move forward on a DOE project that we believe is going to be starting very soon. And lots of future directions for this. It's very exciting. It's a very exciting work, and we're happy to be working with a broader community on this. So I do have a paper, if you're interested on this, that explains kind of what we did. It was presented at the last Hawaii International Conference on System Sciences, and that's the location if you want to get it. I guess we're taking questions at the end, right? All right. Thank you.
Thank you, Tom. I do think Power Flow Whatever would have been a great name for this panel, so we might consider that for next year. So next, I want to welcome Shih-Chieh Kao, who is with Oak Ridge National Laboratory. So going from just power system modeling and weather generally, now going to focus on hydropower. So thank you.
All right. Hi, everyone. I'm Shih-Chieh Kao. You can either call me Shih-Chieh or call me Kao. I actually go by both names. So pick whatever you feel easier. I'm from Oak Ridge National Laboratory. I'm not sure if you know where it is. It's very quick that if you want to go there, just keep driving east 2.5 hours, you will see us. And 1 more hour, you will see Great Smoky Mountain, right? So consider to visit us in the future. So welcome to Tennessee. I hope you enjoy the weather. We typically don't have that. So you guys brought the weather here, right? So this talk will be on hydropower. So I don't think there are many people working on hydropower. I see one there and I know some, okay, yeah. Probably not too many. So I'll start from this map. This is a national hydropower map. One thing our group have been doing for Department of Energy is to maintain an inventory of all existing hydropower plants in the US. So this is based on that inventory. So in the US, there are over 2,000 hydropower plants. Most of them are non-federal. Federal, which is the focus of this talk, is only 132. If you add TVA, that's 30 plus more. So we'll be looking more into there. Just want to have a quick sense of where are the major hydropower plant. Pacific Northwest, no problem. That's the biggest one. Northeast have a lot, and California, Colorado, and we're in Southeast, and there are also many hydropower. Right. So hydropower is great. All right. It has a lot of benefit, in particular like storage, right? So far, pump storage is still the biggest battery, right? We have, right? But the problem for hydropower is it is highly dependent on the water, right? Hydrologic variability is highly unpredictable. I don't think anybody have a solution for drought. We want to have that, we don't. So whether if we know how much water we can plan for is very critical. So this talk is about that. So we have been trying to do that for a while. So so far, this line of research basically looking at how to develop scenario, try to tell us how the future water availability will look like, and also try to use that to tell us extreme event as well. So this particular work, we focus on federal hydropower system. So I said there are not too many hydropower plants, but they are big, in the way that they account for 40% capacity across the US, right? So that's important thing to study. And we have been working closely with several other agencies like Army Corps, Reclamation, and others to looking into the hydropower and related water supply issues here. So the time scale is different thing I want to highlight because for hydropower, we want to know not just tomorrow. We want to actually know further because there's a planning aspect in there. So we are kind of shooting for 2060 each. So to get a water availability estimate to that time scale so far, we believe using output from Earth system model is still the best approach, right? But not directly not the raw output from ESN, which is not directly usable, right? So the trick is how to make all kinds of things to make it usable. So that's the main focus of this research. With that data, then we can link it to extreme event and others, right? And you can also provide a foundation because our sponsor, they have a mandate to provide the report to Congress every 4 to 5 years. Right. So this is the main driver of this research. There's a thing called Secure Water Act. I don't know how many of you have heard that. There are several sections directing different agencies to do different things. For Department of Energy, Section 9505 is the main driver. We want to have a periodic assessment into federal hydropower. So sometimes I will use the acronym 9505 that refer to this study. And my colleague at USBR, they are working on 9503 assessment. It's basically water risk in the entire Western US. And USGS is also working on other sections in the Secure Water Act. Right, so the focus here, as I said, is the federal hydropower. So this map, now we only see federal hydropower and their watershed. And federal hydropower in the US are marketed by 4 power marketing administration. I guess you may heard Bonneville Power, Southwestern, Southeastern, WAPA, that kind of acronym. And so basically, power market by them, and the reservoir are operated usually by Army Corps and Reclamation. TVA is not here because TVA is still federal, but it's not written in Secure Water Act. That's the reason they are not. But we still keep close communication with TVA in this study. All right, so, all right, so what is the process to convert the raw output from GCN to something that usable, right? In fact, there are actually many steps there. And so this is a busy slide. Each of the column here basically shows one important component that we need to think about. Each row here representing each iteration of assessment. So far, we complete the 3 iteration, starting by using CMIS 3, CMIS 5 to CMIS 6 data. And now we are looking into the future, right? Several things to look at it. Like one important step is the downscaling. I think this crowd know more about that. So how to do downscaling, either doing statistically or use a dynamical model to do that. And for our hydropower specific focus, the next step is important. After the bias correction, use that precipitation temperature to run hydrological model so that we can estimate how much water we call runoff is available for hydropower generation. Then we can use hydropower model to estimate that either at a site, at a specific site or at a region, how the hydropower generation will be. Then we can start to help PMAs to do some assessment about the marketing risk. Right, so this is a graphical form. All right, so with each iteration, we have slightly different focus. In the most recent iteration, stakeholder actually raised a question. All right, it's nice that you do a lot of crazy modeling. How do I even trust that? I cannot even trust that, right? Yes, we use a several different model together and how to address uncertainty. So we end up take this approach, what we call multi-model ensemble approach. So why is that doing that? Okay, we start by doing GCA evaluation. We evaluate the performance. We end up working with stakeholders to select 6 GCM. Then we use 2 different ways to downscale, dynamical model and also statistical model. With that, we at the same time use 2 different historic observation data set as a reference to downscale. So that basically becomes 6 times 4. Then we have 2 different national scale hydrological model, each calibrated with similar approach. One is called VIC, the other called PRMS. So then we cannot run it again. It becomes 48. And at the end, Oak Ridge has a hydropower model. Pacific Northwest National Lab, who's also a partner of this study, they have their own hydropower model. So we also run both. So we end up create a big spread of projection, and we can use that to do different type of analysis, including analyzing which is the key contributor to the variance, which you will see that later. So, and that also can support some other analysis I can share today, right? So, right, moving into after you go through this trouble, when you create a big data set, then it's the time you can try to see what the model can tell you. So this, starting from this one, I bet you may have seen a very different way this type of data has been plotted. In this way, we plotted by 6 model. And one side is change in precipitation, and the other side is the change in temperature. It is 40 years in the future versus 30 years in the past, right? Temperature is what you expected. Everybody is saying that. Looking into the future, it's warming everywhere. Yeah. Precipitation is in general, you will say that, hey, because of rising temperature, you have more air moisture holding capacity, you likely have more rain, right? But if you look into model by model, there's no consistency. There's a lot of randomness in there, I would put it this way. So that's also a lesson that why one should not just pick one model. In this type of assessment, you should always pick model and see how the ensemble spread look like, right? One thing you can take a look here is that, can we just use precipitation to understand or study hydropower, right? Okay, the answer is no, right? Because the temperature increase, although your precipitation increase, but their interaction is non-linear, right? Because at the same time, you have increased evaporation and other factor, right? So in this plot, basically by using those to drive hydrological model and to see how the runoff look like. So it's basically the main output we want to see, representing water availability. Right. In general, you can see 6 model. So basically one side is by VIC model, the other side is by PRMS model. This different hydrological model. In general, they have similar response, but they are not the same because of the model behavior and parameters. At the same time, you can see that they did not tell you very consistent projection all the time, right? So that's another problem that we need to think about, how to address those uncertainty. Right, with this, we can also take a further look about other things, like in this case that we can look into the high and low runoff. So high runoff is a 95 percentile daily high runoff, and low runoff is 5 percentile. And I think it's a 7-day running average. So the upper one is high runoff, is near 20 years and the further 20 years in the future, and lower two are low runoff, right? So in general, high runoff actually project to increase. In fact, in the further future, you can see more increase, right? And the low runoff in overall, good news is that in many parts of the US, actually low runoff increase. That means that that's risk for the drought. But still a big part of the US, this selection of model actually shows that they are a decrease in the low runoff. That's suggesting a limited, well, the more risk for drought, right? So that's another thing we have learned so far is that it's slightly counterintuitive for some people, because how come with climate change you will have drought and flood both increase at the same time? But in fact, it is, right? Because this is more like a the distribution is not just simply shift, it's kind of flattened. So you actually have increased probability on both sides. That's the issue here. With this data, we can do other kind of assessment. Like for this one, we look into what is the change of direct evaporation from reservoir, right? So this is not accounted by a hydrological model. What is that when you have a stilling water in the reservoir with increase in temperature, you actually have more direct evaporation. And you may not feel you may suspect that is that really a big amount, right? In a very wet area like Southeast, yes, it's not. But in an area like Texas and Colorado, if you do the calculation, you compare that with the water withdrawal and the other thing, you will be surprised. Actually, the amount of invisible loss can be quite larger than you expected. So we also created some data to propose to support some decision. Right, so with all this, after you feed it into hydropower model, this is how it looked like for 4 different power marketing administration across the US, from BPA, Renewable Power, to WAPA, Western Power, and others. Right, so here, as a slightly complicated plot, each plot basically shows an annual spring, summer, fall, and winter, and 2 bars. The first bar on the left-hand side is to show the spread of the inflow to the reservoir. And the right-hand side is the generation from the reservoir, right? So you can see that in general, after this reservoir operation, actually it reduce the variability, and also it kind of push it back to the baseline, right? So that's not a surprise, because I think in our community, we believe those reservoirs, they can provide us a buffer to kind of absorb some natural variability. So that's expected, but at the same time, you can see that the upper two actually provide more, they actually have different behavior than the bottom two, because the upper two is in the Western US, is snow dominant, larger reservoir, and the lower two are many smaller reservoir in the other part of the US. It is more like a controlled by rainfall. So those part of region will have more risk directly to the change in climate. Ooh, I say that term. All right, so this is overall is how it looks like for all federal hydropower generation. All right, so the other thing to go through this trouble is because we want to know what is the uncertainty, in particular, the choice of different model. And here we use ANOVA as a way to analyze what is the biggest contributor to your variance, right? So conventionally, some people say that climate model is the most important thing. It does show here, selection of climate model actually contribute to the most variance. But surprisingly, in some region across the country, we saw that the choice of power model or the choice of hydrological model actually can sometimes be as important as the choice of climate model, right? So that is the message that it's not just fully controlled by which climate model you're using. The other part of the modeling choice is important too. And this is kind of now by breaking them into different seasons and how things look like. You can see that the individual contributor for other factor other than climate is actually have more contribution in, right? Okay, so overall, this is a very quick go through of the assessment we did. We do have the report if you're interested. If you want to use data, open source, you can download it through Globus. All right, if you have Globus, I do hope you have. You can easily get in. If not, then you can still get it, just slightly slower. The data set is in 4 kilometer. It's 1/24 degree across the entire continental United States. It's daily resolution. We have a variety of variables, but I would say I'm more confident in variables like Tmax, Tmin, and precipitation, because that's a key thing we care about and spend quite some time working on that. Feel free to use it. If you have any question, feel free to reach out to us. Happy to discuss. We have some other additional data set as well, like the one I did not talk about today. Is basically using this to drive a national scale routing model to generate stream flow across the entire US. So if you're interested and need stream flow output at a particular river location, let me know if you don't know how to get the data. I think that's it. Thank you.
Thank you so much, Shih-Chieh. So before I joined Grid Strategies, I was at the Department of Energy, and it's only been a few months, but I have already forgotten our proclivity to talk about our research objectives using the legislative and increasing the litigative section numbers. So thank you for that. And Jake, I hope you know yours. So next is Jake Gentle from Idaho National Lab. We're now going to move over to talk about wind power, specifically for dynamic line ratings. All right, Jake.
All right, so if you have hard questions, I'm gonna point you to Shafil. And if you have really, really hard questions, I'm gonna point you to Ken. So part of this material is from work that we've done over the years that I've led since 2009-ish through 2015. Some of this is reflection of 2015 to 2023. And then luckily, it still matches 2023, 24, and 25 or so. So just kind of want to give you a flashback of some of the things that we used to talk about and that we're still talking about. But first, I have to acknowledge the fact that dynamic line rating, yes, it's a passion of mine. It's something I've worked on for all 15 years at Idaho National Laboratory. But there are so many other options for increasing line capacity that I have to let you know that there are many of them and that some of them might be simpler, just more costly. But I'm going to focus on dynamic line rating. In 2019, published in 2020, I believe, was this chart. And I think it still holds true, at least in relationship. The numbers may have shifted one way or the other, and there might be some new technologies that help fill gaps. But essentially, grid enhancing technologies like dynamic line rating offer you that low cost, high impact solution to relieving grid congestion. But what on earth is a line rating and why does it matter and why isn't it already done and implemented if it's so simple? So I'll start on the main chart, the physical chart. It's quite simple, right? There is a thermal limit to a bare overhead conductor. And there is this relationship between how many amps current that you push through the wire and its resistance and then the temperature. It's very simple. The more current you push, the higher the temperature is, the more it sags. And ultimately, at the end of the day, we're trying to keep people safe, keep the system from failing. So you want to run your conductors as cool as you can. And there's a heat balance equation that kind of describes exactly how to accomplish this. Really quite simple. I remember 15 years ago when I started into this, some of the folks at the time, long careers in transmission line design and ratings are like, yeah, why are you making it more complicated? We have this thing called a static line rating, right? It's very simple. Seasonal adjustments, we design it once, set it and forget it. Well, here we are, still making it complicated. And it actually gets more complicated. And I think the value in the things we're working on is we're solving the complexity to make it simpler with more efficiencies and better utilization rates. So I kind of circled a couple parameters where, conductor parameters matter. So if you're looking at dynamic line rating and forecasting capacity on a certain path, you actually have to know what the conductor is. The voltage doesn't quite matter, but you do have to know what its limits are, the diameter and resistance and impedance and everything else. And then the other set of circles. I'm colorblind, so I'm not going to tell you which one's which. Probably one's red and one's yellow. I don't know. Is where weather matters. I think that's why we're here today, is kind of forecasting weather conditions so that we can rate a line more accurately as our environmental conditions, extreme weather patterns change and shift. This is where all the hard questions start popping up, is like, what's this K factor thing? What do we do when it's like high wind speeds versus low wind speeds? And it's kind of like shifting gears in the car. You have to know which set you're in before you use the right equation. But those are all simple. Those are easy to program, and people have been doing it for forever. At the end of the day, why do we care? It's really this area under the curve. Anything above static, hopefully you can extract more of that blue area. I use blue because it makes sense to me. A lot of people are like, well, that's money. We should use green. Could use green. And effectively, it's when and where and why do we use which forecasting model for dynamic line rating? And this is where it gets really complicated, because it kind of depends. It depends on your topology. It depends on how many observations you have to reflect and compare against your forecast model. What time period are you in? And so I pulled this from stuff we did back in 2015 to 2023, when we were really working through a memorandum of understanding, MOU, with NOAA and Ken and a whole bunch of others that really helped us drive through which of these models we should use, pulling data from the tapes because it was hard to extract them from the files. And I was glad, Tom, you mentioned the GRIB and GRIB2 files, and all the other complexities that I think this whole community has simplified for us dumb power engineers. What do we do with all this statistics information and weather data, and which variable do you use? This type of a chart was useful for those who are trying to understand, well, if I'm going to forecast something and there's all these different models, when do I use them? So I wanted to compare it against a chart that Ken provided us of some of the details of each of these forecast models, something that we kind of worked back and forth. I'm sure there are people in here that know everything there is to know about this chart and then some. I don't, so don't ask me questions too much about this chart, other than the fact that it matches an updated chart from what we did in 2015-ish, and that a lot of the models that were for projected to be updated and sunsetted, like the HER, still exist, if I'm understanding this correctly. There's projections for it to move along and be updated, maybe in more of a ensemble model. But again, our timelines still match up, where we're looking at persistence versus near-term and long-term forecasts. And somebody asked me a while back, certain FERC orders were coming out, what about this like 15, 20, 30-year transmission planning? Dynamic line rating means nothing to us. I says, well, eventually you are within that 15-year window and 20-year window and 30-year window. So why not know about it now? Because in that many years, you might be asking yourself, shoot, I should have looked at my static rating conditions a little tighter, because temperatures are getting hotter and winds are dropping. There's not as much moisture or rain. So why didn't I consider that when I was setting my transmission line parameters when I was building my system? And this is where I think the novelty is. I presented this once where, well, how many weather stations do we need? How many line sensors do we need? How often do we need to measure and forecast? Well, I think we're getting into a point now where some of those questions start going away. Sorry, Tiffany, I think maybe you're going to bridge some things for us, but this is the future of forecasting line ratings. I don't think we need sensors. I don't think we need as many observations as we have today. But again, without them, what do you compare it to? How do you know if you're right or wrong, or when you're right or wrong? And so I'm still very much a very strong and powerful advocate for local observations. Use whatever forecast model you want. If you don't have ground truthing, doesn't matter what type of ground truthing, I'm not sure who's going to believe you. It's not me, because I've seen this go wrong. There's a lot of models in which the further you go out in time, the higher the wind speeds become. It's like, wait a minute, why? And I don't know why. I'm not a climate or a meteorologist, but it happens. And so we're starting to see all of that information being projected forward. And at the end of the day, people still forget, remember all those equations with all the parameters of what matters? We're going to higher and higher operating temperatures in our conductors. When I first started, it was like 75 C to 100 C was your conductor temperature operating range. high temp, low sag conductors or ACSS, now advanced conductors with carbon fiber composite cores, higher percentage of aluminum. They're driving to 200 degrees Celsius operating temperatures. So this one's pretty simple. Wind direction, just a simple parameter. That angle of incidence matters, but at higher conductor temperatures, simple, direction matters, whether it's parallel or perpendicular, pulling the heat out of that conductor. The next parameter, wind speed. Again, makes kind of sense. Higher operating temperatures, higher wind speeds, pulls the heat out. Simple. Some of the things that start shifting gears for a lot of people is absorptivity versus emissivity. I don't know if anybody in this room knows if you're at a utility, what your emissivity and absorptivity values are for whether it be a new build or a 10-year-old line. Does anybody in the room know what those values would be? Anybody want to take a guess? 0 to 1. You could be right or wrong, it doesn't matter. 0.5, 0.5. That's kind of like a recommend, like right in the middle. Seems to make sense. But if you get it wrong and you start operating your conductor at higher temperatures, because you've installed new conductors, and you haven't really went back into the operations process and said, oh, what's our absorptivity value for this? And you just kind of use that standard 0.5, you can kind of see the variances. As you go higher, one of these matters and one of them doesn't. So we published this in a C-grade paper a handful of years ago. We actually did a sweeping survey across the country of anybody who has published their static rating assumptions. That paper is searchable. You could find it. I don't know, maybe just search Jake Gentle, C-grade, ampacity, and you'd probably find it or something. There's not very many of me's, so unique last name. The good part is it's been used quite a bit for utilities to update their line design parameters and their static rating assumptions. And I think it's even more important as we go to higher operating temperatures with less inherent infrastructure safety nets. Right? We're pushing everything we have to the edge because we have the information to do that. So to kind of summarize, there's also a couple other parameters in that set of equations that impact of temperature increases at lower temperatures for things like air temperature, solar flux versus wind speed, again, versus wind angle, wind direction. And this is the one that I like. It makes it really easy to track which one's which and which temperature the variable matters more. This is definitely not something I can speak to. It's not my information, other than the fact that I mentioned earlier that the longer you go in your forecast horizon, it seems at least that air distribution is more positively skewed. And this is where I was talking earlier. I was like, what does that mean? What does it mean to be more positively skewed? I'm really looking for an answer. Somebody's got to tell me what this means. Debbie, what does this mean? Okay, we'll answer in the question then. Same thing as you go further out. This is another scenario we ran with New York ISO on different lines, and it matched kind of what the weather data was telling us to. All right, these are the summaries. You can read the reports. But I really want somebody to answer that question in the Q&A. There's a whole bunch more reports if you want. We've got an endless amount. I was on a call earlier today where one of DOE's most searched sites in the last whatever number of years when it came to transmission planning was a grid enhancing technologies set of sites. And this is a lot in part because of our industry partnerships and the number of papers they've co-written with us. So take a look. There's other topics too, advanced conductors and other things, but thanks again.
Thank you, Jake. Jake teased what we're going to get into next. So before we leave and go into solar, we're going to dig in on wind a little bit. We want to understand more about why is wind forecasting so important for transmission technologies. So please welcome Tiffany Menhorn, VP of North America, Prisma Photonics.
Very much a loaded question. I think everyone's waiting for some rules and regulations around what this looks like moving forward. So Kind of echoing what Jake said, I really think I'm going to speak about, we should have a no electron left behind type of mentality right now with the amount of load growth that we're seeing, and that's across all markets. And I think from the holistic viewpoint from Prisma Photonics, I'm talking about thermal limitations. So there is a next limiting factor. So in speaking about dynamic line ratings, ambient adjusted ratings, Jake did a great job of that overview, but I am speaking about the thermal limits of the line. So just level setting for everyone here. All right, Prisma Photonics. Let me see how this thing works. So we were founded in 2017. We're a grid enhancing technology. So my background is actually in energy markets and trading, which is really funny because I was negotiating long-term PPAs for 2,000 megawatts of renewables in ERCOT and PJM. And I very coyly said, I feel like no one understands physics. So I think that's something that we all have in common here. And so when thinking about how advanced transmission technologies can really be a bridge to what's going to happen in the industry and get more load in the immediate future, that's what we're talking about. So we were founded in 2017. We are focusing on both resiliency of the system and also AARs and DLRs. The technology utilizes the existing fiber network. So for those of you that are aware, we utilize what's called distributed acoustic sensing. So any physics nerds that we have in the room, this has been around for decades. There's distributed acoustic sensing, there's distributed temperature sensing, but we're using the acoustic kind. So when you're thinking about that, we're using one of the dark strands of fiber that's most likely on the high voltage transmission, sub-transmission, typically in the guide wire, and it's typically in the form of OPGW. So there is ADSS, but OPGW is probably the most common in North America and actually globally. I think when you're thinking about how dynamic line rating technologies have entered the industry, this is a good snapshot of what it looks like. So when thinking about the dynamic line rating model and thinking about the equation itself, you need to know tension, you need to know distance to ground, and you need to know, most importantly, wind speed and the attack angle. How this has been previously identified in the industry was through discrete sensors. Discrete sensors, flyovers with drones, conductor mounted sensors, or tower mounted sensors. So what's happening in the industry in general is, how do you double down on the existing assets you already have? The fiber is already in about 50% of all 600,000 miles of transmission that we have here in the US. So what can you do more? You know, I always say quite often that we have a cost to serve model here in the United States. And so with that model, we have to keep rates low, just and reasonable. And so being able to double down on a capital investment you've already put on your system is really important. With that, you see a lot more. So putting a computer in the substation, what we call our beacon unit, can see about 60 miles in either direction. So think about that when you're thinking about continuously looking at wind speed and wind direction in real time. Okay, not to bore you, there's a lot of different use cases here. Probably the one I get asked most commonly is about wildfire mitigation, but I will not get into that. I'm here to talk about dynamic line ratings. So, but there is a suite of options, right? So all dynamic line rating companies in general really are tackling the two biggest issues in our industry, right? We're tackling resiliency in the system and the capacity. And if I were to rank them, I don't really know. So the secret sauce to how we do it, probably what you're most interested in. So when I'm thinking about what we do, right, we use the fiber. So the fiber, and if you're thinking about fiber in itself, because probably, I don't know if there's any fiber experts in the room, comes in a bundle, right? So comes in a bundle of spaghetti strings. We take one of those fibers, which is typically used for relays, communications, et cetera, and we're powering the entire system. So what we first do is start by receiving the data. So we receive the raw data, the seismic data from the fiber itself. That looks like the bottom right side of your screen. This is what we call our waterfall image. So if you're thinking about raw seismic data and we're putting a laser into the fiber at a rate of 2,000 times a second, we're measuring what's called the relay backscatter. Did I lose anybody? I knew it. I knew it. I knew it. So he wants me to fix wind forecasting. So we're trying to do that. So then what we do, we measure those spectral features and then we actually clean them. So we clean out all the noise in the system and basically look at the acoustic footprint that matters for all those different use cases on the previous slide. So don't fall asleep yet. This is where it gets good. So then we chunk them into spans. So when you're looking at what we're able to do with one beacon unit in the substation, we're looking at the entire line or 30 miles to see whether or not what the wind looks like. So I know this is like crazy stuff. I started this in 2020. And I have to tell you that this is just absolutely phenomenal stuff. So then we ingest that into a machine learning model. Thankfully, there's some really great data scientists that are able to look at this in real time and really measure and calculate not only wind speed and attack angle, but also the effective wind, which is, again, most important for DLR. And we do that on repeat. So probably what's most important to you is how we validate accuracy. This is a wind and forecasting symposium. So when thinking about what we're able to do, we need to realize a ground truth. So with that, the calibration for our system takes a ground truth of putting an anemometer in the field. Using that anemometer in any sort of geographic location that my very smart meteorologists pick, we put those on the field to make sure that we have a ground truth so that we can tell the mean absolute errors of wind speed and wind direction. So let me use an example. So when you're talking about the topography of the land, it is so vitally important that we're measuring every span and we're continuously measuring. And I'm going to tell you the differences of having a weather station in the field versus being able to measure that on the fiber itself. This particular slide is one of our TSO partners in Europe. The reason why this is really an interesting use case is because if this goes from the coastline to the mountains to the valley, it's only a 5-mile line, but this covers a lot of territory. I mean, this is small. Okay, so look back at that slide. So we have weather stations that this TSO, in fact, put on their system. So great, I'll use your weather stations. Let's get a baseline truth. Let's see what we're doing. Let's see the difference of continuously looking at weather data versus looking at it at these points. Weather station number 11, more coastal region. Weather station number 12, more mountainous. Those are the two we're going to focus on. All right, windrows, what we all dream about. Okay, so if you're looking at image number 1, that's the physical weather station in the field. Okay, image number 2, third-party weather data, Meteomatics out of Switzerland. Anybody know them? Great. And the third is a high resolution, the Euro 1K model. So what we're seeing in this image, and this is a coastline image, right? So this is a coastline weather station. What we're seeing is the weather station in image number 1, which is in the top middle. We're seeing that the wind is moving, right? More in the southeast region, right? Little bit in the northwest region, but mainly in that region, which is very similar to the attack angle the Euro 1K is looking at. Really interesting. Coastline region. The bottom part of this slide is actually showing you the wind speed. This again strongly correlates with, and this is including our fiber measurements as well. So our fiber measurements, it's the red number, the red color, and then the Euro 1K being the yellow. That is really the takeaway here, is looking at how similar those are and how the accuracy needs to happen at really the span level. Even more interesting, a valley-oriented wind. So if you remember, weather station number 2 was kind of in the mountains, in the valley a little bit. The valley is really protecting that wind. And so thinking about where transmission corridors are, especially in image number 1, we're seeing the wind moving from west to east and east to west in either direction, but that valley is really protecting any sort of variance in that wind. Again, looking at 2 different wind models, very different case when it comes to the windrows. Pretty cool stuff, right? Everyone's supposed to say yes collectively. It's the end of the day. We can do this. We can solve grid constraints. Okay, so the other thing that's really exciting to me, maybe not exciting to everyone here, is the attack angle and how we can see the attack angle in real time of the wind and how it moves throughout time and space. Okay, so when you're looking at this, this is about 130 different spans over a period of time of, I don't know, I'll have to look at my notes to find it, but it's about 130 different spans over 1 hour. Okay, x-axis is speed, x-axis is span, y-axis is speed. Okay, what is this showing you? This is one of our partners in the US market. This is a really interesting long line. This is 30 miles, actually 30 miles in one direction. So what you're seeing here is the red is indicating the really strong wind, and the lighter colors and the blue especially is indicating a light wind. So what does that mean? So when thinking about how wind is effectively moving on your line and what kind of constraints that the attack angle actually looks at, and that's exactly what we're seeing. So not only are we seeing wind speed, and the wind speed actually fly across the southern portion of this line, we're actually seeing the wind change dramatically when there's a sharp angle. So the same wind attacks the line at two different angles, the blue meaning low wind speed, red meaning high wind speed. This is a very big issue with dynamic line rating. This is something we need to be looking at in real time, why continuous monitoring is so vitally important. So now we add in, you might be thinking to yourself, what does the actual land look like on this line, right? This is Southeast region of the United States. Well, this is what it looks like. So image number 1 in the bottom half of the screen. So if I'm looking at that and pointing to where the strong winds were, there's nothing there. There's no trees, it's flat. There's that one tree. That's where the highest winds are. If I'm looking at image number 2, that actually is an image in the north and south directions. And you can see one side is actually shielded by trees. The other side is not. You can see the high wind speed and the lower wind speed. The third image, same locations, looking at north and south, seeing that variance at that corridor, right? Seeing the low wind speeds going north and the high wind speeds going north and the lower wind speeds going south. This is something that we're able to do in a 15-minute increment for utility partners. Why is this important? Because the dynamic line rating model is something that you're going to want to use in operations, and the forecast is only going to be up to, my argument is 48 hours, but we'll see what happens with FERC. All right. You might be thinking to yourself, this might be the world's longest wind measurement device, but I don't know if it is or not. So you'll have to ask ChatGPT on that. But what I do know is comparing what we're able to do in a continuous manner versus discrete sensor is really unprecedented. So we're talking about a mean absolute error of wind direction about 15 degrees and wind speed under 0.46 meters per second. These are extremely accurate numbers that we're getting to in the industry. And this is why you want to be looking at a continuous span and you want to be calculating your DLR accordingly. Again, we'll see what happens, but very excited to answer questions, and come find me in the orange jacket later if you want to talk more.
Great, thank you so much, Tiffany. So last, we're gonna move into solar. I want to welcome Hoai Nguyen of NSMO from Vietnam. Thank you for making the long journey, for being here today to talk to us. And then after this, we'll get into Q&A. So please, everyone stick around. Do you want to walk?
I think I can move some. Good, right?
Yep.
All right.
So good afternoon. My name is Hoai. I'm from Vietnam. Yes. So before I talk, I will start to thank Debbie, thank Isaac to give me chance to talk about this session. And you know, I come from Vietnam, so it's take me 30 hours from Vietnam come to here. So I want to talk more, explain more, talk more with you guys before I have 30-hour flight back to Vietnam. So that's why Debbie arranged for me this session. To me, to talk about what happened in Vietnam in the last few years in terms of power system and what solution we have. All right. So before I start, I would like to introduce a little bit by myself. My name is Nguyen. I'm working for Vietnam's TSO, the company's local national power system and market operators. We are the person who operates the power system at national levels. I'm working for this company for 13 years, 13 years. And so right now I'm the team leader of the forecasting team. Today we talk, we listen about our colleagues from AEMO, from AirCost, who do the forecasting teams. I am the one who do the same thing in Vietnam. So yesterday we have catch up. Very easy to talk because we just doing the same job, just different country. All right, now I'm going to give you an overview about what happened in Vietnam in the last few years in terms of renewable energies. Vietnam is a developing country. We have the population of 100 million people. That is 13 in the world. Installed the power system, we have very big power system. Installed capacity 85 gigawatts, and the big load is 48 gigawatts. Compared to the world, we're number 21 in the world, and we're developing countries. What I like to highlight in this slide is just our loads average growth about 6 to 7% per year. This number we take into account the COVID. Without the COVID-19, so our loads increase about 8 to 10% per year. What does it mean? It means that after 7 years, our power system will be double. So that's a very big pressure for the governments to have more and more generation. So the big question for us now is how to have enough generation. So that's why the government give very good feed-in tariff in 2017. So let's say that in 2018, we have zero renewable energies, but after only 3 years, 2019, 2020, and 2021, we have 21 gigawatt of renewable energies. We take 28% of installed capacity for whole country. The number we have here is excluding the small hydro. Small hydro is developed from a long time ago, but for the in 3 years, from zero renewable energies, we have 5 gigawatt of wind farm, 9 gigawatts of solar farm, and almost 8 gigawatt of solar rooftop. So it's puts very, very much big pressures for the operation company like us, because the renewable energy just come in the short time. As you see on the map, yes, the areas that I put the circle is the areas which have really good wind speed, really good irradiance. So the biggest issue is just all of the solar farm, wind farm, solar rooftop located in this area. So in 3 years, we have 21 gigawatt and is on in a certain areas, which makes us have the overload, the curtailment in the local areas and also on 5 kV slide backbone. So that's asked us to have to come up with the solution as fast as possible. So the solution I am going to talk with you right now is solutions that we come up with ourselves. We do not have time to looking for the vendors, looking for someone to build a proper tool for us. We have to do this by ourselves. All right. So in here, we have 3 solutions. The first is satellite image. That is the solution we have to solve the issue with the solar rooftop come very fast. The second thing about forecasting combinations is a solution we have for the wind farm and solar farm. And AGC is something that we have for the overload areas. I will go step by step. All right. Firstly, for solar rooftop, the sizing of the solar rooftop, as I mentioned with you before, that is 8 gigawatts in operation in just 1 year. So it strongly affect to our power system. Our load forecast cannot be correct. Renewable energy forecast cannot correct. The planning, the real-time operations must be got the data from the solar rooftop. So the question right now is, how can we get the solar rooftop data? Get more accurate data. So we came up with a solution. Just we use the satellite image. We have the satellite image we call Himarawari Nice by Japan. They give the image, satellite image. So we hire vendors, the local vendors, to analyze from satellite image to give us the irradiance for whole country with the resolution of 2 times 2 kilometers per point. So it means that's very detailed for the country. Since we do the simulations for all 110 kV substation, we have installed capacity, we have the irradiance for the near real time, which is almost can say the actual irradiance, and we can calculate to the megawatt and the energies for the 110 kV substation for the whole country. And this is clearly talk about what we're doing from Himarawari satellite image. We have a server, we have providers from Vietnam, they analyze data for us. They send us the irradiance for her whole country with 2 times 2 kilometer resolution. And it's 40 to 60 minutes later than actual because it's the time for analyze the data and it's sent to us and we can have the estimate, the gross megawatts power of solar rooftop for the whole country. This is the tool we have done. The tool we have done by ourselves, all 110 kV substation in the country, which is more than 800. And the data for the solar rooftop is 40 to 60 minutes later than actual. As you see on the map here, that's all the data we have from the satellite image, 2 times 2 resolution irradiance. With the red color, the orange color, it means that the irradiance is very good. All right, so that's what we done to have the, let's say, just near real-time actual megawatts power for the solar rooftop. The second thing is we got about the forecasting. When we have more renewable energies, the question is about how to get the forecasting. Just what's the AEMO, what's the egg cost, what the guys shows, all of this operator company we had to do. So for us, we have done the same things. Is in here, you can see on the right-hand side, that is the forecasting source we're having right now. We have 2 third-party suppliers. It means that we buy the forecasting from other company who do it for us, and we have vendors. Let's say we have the bids every 2 years, and right now our suppliers is one from Spain, one from Germany. So what they do is that they do the forecasting for the whole country, whole of the 250 solar farm and wind farm plant in Vietnam. The forecasting for each of them. And the third sort of forecast is we have in-house forecasting. Yesterday, Adria from AEMO, he said that they do some black box algorithms. For us, we do the same. We do black box, we do white box algorithms to have the in-house forecasting. And we also asked the power plant to do send us the forecasting. But now the question is just, we have 4 sorts of forecasting. How to take the best out of this? So that's why we come up with the ideas. We build the forecasting combination system, which run online, which calculates accuracies for each sort of forecast online every 15 minutes, and it's going automatically, let's say, just propose to us the best forecasting values for each plant. In here, there one point I would like to highlight here, the forecasting resolution will reduce from 30 minutes to 15 minutes. Just is reduce the forecasting resolution. That is the best way to include to enhance the forecasting accuracy. So in 2013, 2023, we have done to reduce all of our forecasting models from 30 minutes to 15 minutes. All right, this is the algorithms we do for the forecasting combination. This is real-time running. This is tuned for our system operators. and the accuracy have improvements quite clearly. In this case, as other TSOs, you want to talk more about these algorithms, I'm happy to. All right. So now we talk about the overloads, the curtailments, how we do it. As I talk with you, the curtailments were very bad. We have curtailments in certain areas. We have a curtailment in 500 kV transmission line backbone from north to south. So the thing is that the investors for the solar farm, wind farms, that is from all the big companies. So the question for my companies is how can we do the curtailment equally to own the plants? We cannot do it manually, or we cannot do something that is not clear. So the solutions we have come up is we using AGC. Normally, you heard AGC, that is something to send the control dispatch orders, to do the frequency controls, to do the tie line bias, something. But in Vietnam, we use AGC, automatic generation control, to control all the solar farm and wind farm plant in the country. Meaning to say that in a certain areas, we just have 110 kV transmission line, but it have about 10 solar farm and wind farm in this area. So it's got curtailment from 10 to 2, it got overload. So what the algorithm is do? It's like the grid stated. It means the currents through the transmission line. So it's to see how much power that owns other plants in the area can increase or decrease to keep the current level as about 90 or 95% of the rated power. So we use AGC to calculate it online. Calculation would be done every 4 seconds, and the control signal sent to all the plants every 8 seconds. So at this time, we do have very clear algorithm, which have a machine that's done automatically, so no one can complain us. So this is quite something big we have done. All right, so this is some let's say some GUIs we have done in AGC. This is online control, so overload areas in 210 kV substation network, and also in 500 kV network. So this is something is quite special that my company have done. All right. In the last sessions, for the information, the last sessions I also had talked in another room. I have mentioned just in our master plans, in order to get enough generation for the country until 2030, our renewable energy is going to, for the country, from 21 gigawatts now is going to 70 gigawatts. It means that in 5 years, we're going to build 50 gigawatts of the renewable energy. That's in our master plan is mentioned, the government trying to do it. But what is the big question for us now for the operation coming in us? What we need to do? So the solution before this, when the issue come, we have to come with solution immediately. But now we need to think about in the next few years for the operation coming in us, what we need to do. So we're thinking about two things. The first thing is a DERM system. DERM is a system that's in the sort of distributed energy resource management system, meaning to say that this is industrial product provided by big guns in the market, such as Siemens, GE. They have this product and is to manage, to control all the solar farm, wind farm, solar rooftop, everything, the battery storage, and also the EV, everything. The reasons I propose this idea is just all the solutions I have talked before is something that we do by ourselves. But we got the issue is that the solution we have done by ourselves, can it talk with other hardware in the company? Can it expand the capacity or not? In the next 5 years, I'm not sure. So now I want to buy it from some third-party supplier, from some big guns in the markets to give us product which easily can talk with any other hardware. So this is a question for us right now. We are not sure just we're going to buy the dome or not, or we are going to develop by ourselves. So in support of GBSD, Mr. Shang here, we're going to have a workshop on the dome and AI applications, which will be done in Hanoi, in Vietnam, in October 2025. So I would love to invite you to any of you, if you want to know about the topic, just give me a message. So maybe we will invite you to come there and we can talk together. So I'm really looking for the chance, just TSO from all around the world. We're doing the same job, but it's difficult to talk to each other. We sit at the same table, same room. We talk together about what's going to happen. All right. The second solution is was the thing we call enterprise service bus. Or for the guys, I see you have done it, which called enterprise service bus. This means that is a big bus for all the hardware, all the software in the company. We can talk together. Yes, so this is a solution we are looking for. And the message bus or enterprise service bus, also platform for the TSO can talk with DSO, because now the distributed energy is more from distribution side. So communication from DSO to TSO will be more and more important. So we are looking to this solution also. Yeah, so that's all of the idea right now. I've talked about the solution we have done in Vietnam and some open question about what we should do. So thank you very much. That's all of my speech.